in this problem, this is the requirement. Okay, the line regulation should be 40 millivolt by volt, load regulation to be 5 millivolt by milliampere, and this is the output voltage of the regulator, which should be 15 volt, and the range of the input Vs is from 20 to 30 volt. Okay, so in one of the tutorial class we have discussed that the load regulation is equal to the RZ of this Zener diode. Okay, so this my load regulation. So in any regulator, so load regulation is equal to the RZ. Okay, and already it is given that this is 5 millivolt by milliampere, so which is basically 5 ohms. Okay, so this we have discussed already in one of the tutorial. Okay, and what is line regulation? Line regulation is how much the output voltage is varying. Basically, this output voltage is varying for a given change in the input voltage in no load condition. And this also we have seen in the tutorial that line regulation is basically given by RZ by RS plus RZ. So basically, which is, if again this is also from tutorial. Okay, so what we had seen was that if there is a change, okay, and I have my RS here, the small signal analysis of the the load regulator, right? If there's a change, basically change in the Vs, then my change in the output voltage will be given by the this resistive divider kind of configuration. So this is given by RZ RS plus RZ, and this value is also given which to be 40 millivolt by volt. So this ratio is basically, you can say that it is it is 40 millivolt by 1 volt. So if milli comes down, so it is 1000. Okay, so now if I just substitute the value of RZ, therefore my 5 RS plus 5 ohms is equal to 1 by 25. Okay, so implies if I just solve this equation, just multiply it and add, my RS comes out to be 120 ohms. Okay, so this one. Okay, so the next thing asked is, so we already have the two value asked. We have got this RZ and we have got this RS. So now next we need to find out, of course we are asked to find out what is the VZK, okay, and IZM. Okay, so the typical output voltage is 15 volt. Okay, so the VZK is basically where my diode starts breaking down. So because my output voltage requirement is 15 volt, so if we say that VZK is around 15 volt, that is also fine. Okay, and of course you have been asked that VZK, VZK and VZ0 are approximately the same. So if someone has written that the VZK should be around 15 volt, that's absolutely fine. Or someone have done a little bit calculation, using the IZK and all, which is also around the value, that has come to be around 15 volt, that is also fine. That is also accepted. Okay, so since my typical output voltage 15 volt. So the Zener diode should also break down in that region. Okay, so that means my VZK, which is approximately equal to VZ0, will be approximately equal to 15 volt or near around. If someone is taken a little bit above or below, that is also fine, that is accepted. Okay, so now and now we need to find out. So we of course the VZK is also this one, and now we need to find out what should be my IZM. Okay, so to find out IZM, my this VS should be okay. So basically the IZM, if you have to find out the IZM, generally the load is not connected and this RS is selected such that the even if there is no load, the maximum current flowing through this diode is lesser than IZM. And in this condition, we also have discussed multiple times the VS should be maximum. Okay, so for finding out calculating IZM, so this will be my circuit. Okay, so I have my VS as 30 volt and we already know this RS, and there will be no load condition. Okay, and we have, if I replace this model with the VZ0 and RZ, and what we are telling is that in this condition my my maximum current flowing is IZM. Okay, so I want to know what is this current flowing. Okay, so this RS has been selected such that that IZM is even if it is highest, then I want to know basically the maximum current that is flowing. Okay, so through this, so then in this case IZ will be equal to, okay, so of course this is 30 minus the VZ0, which is 15 volt. Okay, VZ0 by these two resistance, which is RS plus RZ. Okay, so in this case it will be 30 minus 15. So RS is RS is 120 plus 5. So if you calculate this value, you will get 120 milliampere. Okay, so that means when no load condition is there, for the selected value of for that RS, my IZ is 120 milliampere. So for a specification, I should select a Zener diode whose IZM maximum should be greater than or equal to 120 milliampere. Okay, so or even if someone is taken it to be 120 milliampere, they will get full marks. Or if someone is written greater than 120 milliampere, they will also get full marks. Okay, so yeah, so this is the next answer. So now we need to find out the minimum value of RL. Okay, so let's try to see the circuit, how it looks like. So for the minimum value of RL, of course, we just need to make sure that the Zener diode has just broke down. And we also have discussed multiple times that it should be the minimum voltage. So it is 20 volt, and of course this RS is fixed. Okay, and of course if I throw the diode, okay, so in this case a minimum current is flowing. Okay, so whenever we are finding out the minimum value of RL, minimum value of minimum value of the diode current should flow. So in this case it will be IZK. Okay, so IZK will be flowing through this. Okay, and of course in this condition here it will be VZ0 and VZ0, and of course we can find out the current flowing through this IRS. And once I know what is IRS and IZK, I can easily find out what is my IL. Okay, so let's do the calculation. So in this case, IRS will be equal to, we know this voltage, we know this resistance. So it is Vs minimum minus Vz0 by Rs. So this comes out to be minimum is 20 minus Vz0 is 15 volt. Rs, we know that it is 120. Okay, so if we do this calculation, of course 120 ohms. Okay, so this comes out to be around 41.7 milliampere. Okay, so now this is the total current and it is getting divided from here to here. So therefore my IL will be equal to IRS minus IZK. So this comes out to be 41.7 minus IZK is already given in the problem, 20 milliampere. Okay, so this 0.2 milliampere IZK is given in the problem statement, 41.5 milliampere. Okay, so therefore my RL minimum will be equal to Vz0 by the current flowing through this IL. So this is 15 by 41.5 milliampere. So this comes out to be 361.4 ohms. So those who have got a value of around 360, right, 360, 362 or 363, they will be rewarded full marks. Okay, so this is the end of the solution of the end of the fifth problem, right? We have calculated the VZK, IZM, RZ, and of course RS, and also found out the minimum value of RL. Okay, in the next problem we have been asked to find out all the different currents through all the different branches. Okay, so let's give name to some of the nodes, which is important. Okay, let's call this node to be maybe Vx. Okay, voltage at this node to be Vx, and let's call this to be maybe Vz. Okay, and maybe this node to be Vy. Okay, so now first of all you have to find out which of these two transistor is on, and we know that when a transistor is not in a cutoff region, when it is an on state, the base to emitter junction behaves like a diode. Okay, so we will be using this phenomenon to solve this problem. Okay, so the base emitter junction or the BE junction of a BJT can be treated as a simple diode. Okay, so we will be using this simple simple phenomena to solve this problem. Okay, so now if this is just a diode, so I have two diodes here. So either, but the other end of the diode is of different voltage. So we already have solved a problem of if I have a resistor and if the two nodes of the diode have the different voltage, like if this is 3 volt and if this is 5 volt. So this is quite similar to this problem, right? I have a 2 diodes, so 3 volt and 5 volt. Okay, so the only possibility is that only one of these diode will be on. Okay, so both of these diode cannot be on, and we know that it's very clear that, you know, so if the higher voltage one, it will be on and this will be off. Okay, so let's consider this case 1. Okay, case 1, if the base emitter junction of, let's consider the Q1 is forward bias, then my Vx definitely will be 5 minus 0.7. Then Vx is equal to 4.3 volt. Okay, then the base emitter junction of Q2 will be in reverse bias region. Okay, so when this is at 4.3, this will be in a reverse bias condition. Okay, so case 2 can happen that if the base emitter junction of Q2 is in forward bias region, then my Vx will be this Vx should be 2.3 volt. Then the VVE junction voltage of Q1 will be greater than 0.7. Okay, so which is not possible, right? It cannot be greater than 0.7, hence only the case 1 is valid. Hence case 1 is only possible. So my Vx will be 4.3 volt. Okay, so it is clear that my current flowing, so this is in cutoff region, okay, and this is in the forward bias region. Okay, so now if we see here, so because it is in cutoff region, my current, my IC2 is going to become 0. Okay, so if my IC2 is 0, my this IC and ID is 0. Okay, so therefore my IC2 is 0 and also my IC and ID is equal to 0. That's it. Okay, so now since I know this voltage Vx, so I can now easily find out this current IE. Therefore, my IE voltage will be equal to Vx by, we have this resistance, let's call it as Re. So the resistance Re is equal to Vx is 4.3, and this is 1 kilo ohms. So this is 4.3 milliampere. So this is the next solution. Okay, so now my IE is there. Okay, IE, and of course this IE is equal to IE1 as well. So my IE1 is equal to, therefore IE1 means the emitter current of this transistor flowing through it is also equal to same as IE, because there is no current flowing from this part. So of course I can now easily write, I can know the IC1 of this Q1. So since from the transistor equation we know that since my IE1 is equal to the summation of IB1 plus IC1 of this transistor, okay, this transistor. So what I can write is IB1 is, I know that it is IC1 by beta plus IC1. So therefore if I try to find out my IC1, it will be, if I just rearrange this, I will get beta by beta plus 1 into IE1. So now if we just multiply this, beta is given to be 100 in the problem, and beta plus 1 is 101 into 4.3 milliampere. So this comes out to be 4.26 milliampere. Okay. Okay, so now here we have almost solved the problem half. So I have found out this current, this current, this current. So now I have found out what is the current flowing through this. Okay, basically my IC1. So which is summation of IB and IA. Okay. Now if we see this diode, okay, let's give this name, diode a name. Let's call it as D1, D2. So if you see this diode D2, this voltage is always connected to the higher potential 10 volt, and this voltage will definitely be lesser than 10 volt, right? Either at max it can go, if no current is flowing through this, at max it can go at 10 volt, but it can never be more than 10 volt. That means D2 is always in D2 is always in off state or in reverse bias condition. Okay, so let's say that. Okay, so DT will never be turned on. D2 is always off. Okay, so D2 is always off or in reverse bias region. Okay, so this is directly this we know that this we can directly get it from the inspection. Now we don't know about this D1, whether it is in the off state or it is the potential here is in the on state. We don't know about this D1. So let's assume that D1 is in the forward bias region and in the on state, and that's why the D1 there will be a voltage drop of 0.7. Okay, so let's assume D1 is in forward bias region. So here we can add one comment, because Vy is always lesser than 10 volt. Okay, the supply. Okay, so let's assume D1 is in the forward bias region. So if we assume the D1, this one to be in the forward bias region, so I can draw this whole thing something like this. Let's redraw it, this one. So I can redraw this whole thing something like this. So I have my this resistance and I have my this diode, okay, which is 0.7, and this diode is open, okay, and I have another resistor, okay, and so this is my 10 volt, okay. So let's let's name this resistor. The current flowing through this is Ig. Let's call it as Rg. Current flowing through this is Ia. Let's call it as Ra. And current flowing through this is Ib. And let's call this resistor name as Rb. And this, we know that this is not Vy and this is not Vz, okay. And current flowing through this one is IC1, and we already have calculated this value, okay. So now let's assuming this to be in the forward bias region, let's do the calculation. So now if the voltage drop across here is 0.7, that definitely, therefore my Vy is equal to 10 minus 0.7, this is 9.3, and of course we can just easily find out Ig, therefore my Ig will be equal to 10 minus 9.3, which is 0.7, by this is Rg, which is 1 kilo ohm, so it is 0.7 milliampere, okay. So yeah, and now we know this voltage, and we can find out this these two current. So the summation of, we know that Ia plus Ib is equal to IC1, and it is coming out to be 4.26 milliampere, okay. So this is one of my equation. So let's call this as equation number 1, okay. And if you see here, this voltage Vz I can write in two ways. So Vz is nothing but, if I see from here, this is Vy minus IaRa. So this is Vy minus IaRa, this side, and this side it is equal to 10 volt minus Ib Rb, okay. So now here I have two equations, right, of IAIB, this one and this one, and I can just simply solve these two and get it, okay. So implies I can write this as Vy, we know that it is from here we know that it is 9.3 minus Ia, okay. So Ia Ra is equal to 10 minus Ib Rb. So implies I can just write it as Ib Rb is equal to, if I take this side, so, or basically I'll take this side and I'm taking this side, so 0.7 plus Ia Ra. So if I try to express everything in the milliampere, so I can just so then I can just use kilo ohms for the Ra and Rb. So then the currents will be always in the milliampere. So this is 1 kilo ohms. So Ib into 1 is equal to 0.7 plus Ia into, this is 5 kilo ohms, okay. So this is my equation number 2, okay. So solving 1 and 2, if we just solve this 1 and 2, what we will get is, we'll get IB as 3.67 milliampere and IA is equal to 0.59 milliampere. Okay, so this is my IA and IB. This is how we have solved. Now, if we see here, if we see, go back to the question, if we see here, we have been asked to find out the current through the diode. Okay, so which is basically my IF. So now what is IF? IF plus IG also we have calculated. We have calculated everything. We have calculated IF and IG, and IF plus IG is equal to IA. Okay, so IF is the diode through this current. This is IF. Okay, so since IF or IA is basically IG plus IF, implies my IF is equal to IA minus IG, and IA we have calculated to be 0.59 or approximately 0.6, and IG we have calculated it to be 0.7 milliampere. 0.7 milliampere. So this comes out to be negative 0.11 milliampere. So the sign here negative means that the direction of IF is reversed. So the direction of IF is reversed, which is not true. That means that assuming this to be in forward bias region is not correct. Okay, so that means this is in the cutoff region, means the potential drop across this RG is not sufficient to turn on this, means it is lesser. Okay, so D1 is not on. Okay, D1 is not on, it is off. Okay, of course it's not in the reverse bias region, but it is the drop across this one is not 0.7, it is lesser than 0.7, and on the question we already have told that the diode should be minimum 0.7 to be on. Okay, so then we can say that it is off. So now my whole circuit will be something like this. I have my, this one is RG, so this diode is also off, both this D1 and D2 are off, and I have my this is 10 volt. Okay, so this is IC1 and this is IB, this is IA, RA, RB, and this is my IG. Okay, so in this case this both are off, so my IA is equal to IG, IA is equal to IG. Okay, and it is just a simple problem of the current flowing this and this, so we can easily find out the ratio. Okay, so therefore my IA is equal to IG is equal to, we know that in this case, if I want to know the branch, like two parallel resistance, and if I want to know the current in this branch, then it will be RB by the total resistance in this branch, which is RA plus RG plus RB into IC1. Okay, so if I just put this value, this is RB is 1, RA is 5 plus 1 plus 1 into 4.26 milliampere So this comes out to be 0.6 milliampere. Okay, and IB is equal to the resistance in this total part, which is RA plus RZ by RA plus RZ plus RB into IC1. So if you substitute this value, this comes out to be 6, 1 plus 5 plus 1, and this is 5 plus 1 plus 1 into IC1, it is 4.26 milliampere. So this comes out to be 3.65 milliampere. So these are the final answers of this problem. So here a circuit of two diodes have been given, and you have been asked to find out the voltage transfer characteristics. Okay, so whenever you have been asked to find the voltage transfer characteristics, you should vary the V in from minus infinity to plus infinity. At least you should imagine that it's going from very much negative value to plus positive value, and then you need to see what are the conditions or when these two diodes will be on and off. So let's start with really negative, really negative, or maybe from 0. Okay, so let's consider this point, this voltage, to be Vx. Okay, so now if this V in is very negative, much lesser than 0 volt, obviously this diode D1 is going to be in the reverse bias region. Okay, it will never be in forward bias region, but this D2, this general diode, will be in forward bias region, and of course the drop of D2 will be 0.7. Okay, so and this can happen when this Vx voltage, or this Vx voltage, or basically we can say that this V out minus Vx voltage, this voltage is 0.7, then this D2 will be on. Okay, so for that, let's try to find out at what voltage of this Vx this diode will be on. Okay, so let's try to estimate what is this voltage Vx. So assuming that maybe this V in is very close to 0. Okay, so when V in is close to 0, when V in is close to 0, okay, V in is very close to 0, both this D1 and D2 are not on. D1 and D2 are off. Okay, D1 and D2 are off, and I can write it as so Vx can be written as, then Vx will be given by so it's a simple resistive division, so it will be R2 plus R3 by R1 plus R2 plus R3 into V in. Okay, so now we already know that this R3 is very small compared to R1 and R2, and I have asked you to assume that if one of the resistance is very small, then the bigger resistance dominates. Okay, so this can be easily written as R2 by R1 plus R2 into V in. Since R2 is much greater than R3, and again R1 is also greater than much greater than R3. Okay, so now if I just substitute this value, so this is 10k, and this is also 10k plus 10k into V in. So this is basically V in by 2. Okay, so my Vx is obviously, it's obvious because these two resistance are dominant. It's a very small, so it's a simple resistive division. So now D2 will be on if V out minus Vx will be 0.7, means Bx is smaller than V out by 0.7. So D2 will be on if V out minus Vx is equal to 0.7. Okay, and what is V out? So if this voltage is Vx, V out will be just a resistive division. Okay, R3 by R2 plus R3. So R3 by R2 plus R3 into Vx minus Vx equal to 0.7. Okay, so okay, if we substitute the values here, of course R3 is much lesser than R2, so we can directly approximate. So R3 is, we know that it is 100 ohms, and this is 10 kilo ohms plus 100, and Vx minus 0.7. So this comes out to be because I can easily make it 10k, because this 100 ohms is much lesser than 10k. So then this ratio comes out to be 1 by 100, Vx minus Vx equal to 0.7. So if you see here, this is 1 by 100 of Vx, so Vx is minus 0.7, or if we exactly, even if you calculate, we'll get as Vx equal to minus 0.69, or which is approximately which is same as I should say that even if you approximate as 0.7, that is also correct. So now Vx is we know that Vx is V in by 2, so therefore V in is equal to 2Vx. Okay, so which is equal to, you can write it as minus 1.4 also is correct, or you can write 1.38. Okay, so if you have approximated to be 0.7, this 1.4, or you can to be more precise, it is minus 1.38. So when my V in is lesser than minus 1.38, this diode is on. Okay, when this is lesser than minus 3.8, this diode is on. Before that, both these diodes are off. Okay, so when this diode is on, so this is what we are going to get. So when V in is lesser than minus 1.38, so D2 is on, so this is what I'm going to get. This is my R1, and this is on. Okay, this is my V out, and this is my V in. Of course, this is my Vx. Okay, so I can easily calculate now what is my V out. Okay, so there are different ways to calculate the V out. If we say that the current is flowing in this direction, that also we can write. Okay, so if I say that you can solve a simple KVL. Okay, so if the in this case, of course, the current is actually flowing in this direction. Okay, so if the current is flowing in this direction, okay, so of course this is R3, so therefore my I will be equal to the voltage here, which is 0 minus 0.7 minus V in by, this is R1 plus R3. Of course, this R3 is much smaller than R1, so this becomes minus of V in plus 0.7 by R1. Okay, so therefore my V out will be equal to, so the current flowing through this is I, and IR drop is V out, but of course the current is flowing from 0 to V out, so a negative is going to come. Okay, so minus IR 3. Okay, so minus IR3. So that's why, and what is I is this one. So, and minus IR3, so the negative negative gets cancelled, so it becomes V in plus 0.7 R1 by into R3. Okay, so yeah, so therefore my V out, if I put the value of R3, this is 100 and this is 10k, and this is V in plus 0.7, so which is 1 by 100, V in plus 0.7. So this is the case of my V out when my when my V in is lesser than minus 1.3, when V in is minus lesser 1.3. Now when V in is more than 3, of course, when V in is greater than minus 1.38, of course, in that case both the diodes are off, so I have simple voltage division then, R1, R2, and this is my V out. This is R3. Okay, so V in. Okay, so therefore my V out will be simple voltage division, which is R3 by R1 plus R2 plus R3 into V in, and of course this is much lesser than 100 ohms, so this is much lesser than R2 and R1. So even if I put the value, this is 10k, 10k plus 100 V in, so this comes out to be 1 by 200 into V in. Okay, so this is the case when when both the diodes are off, so V in is greater than minus 1.3 volt. Okay, so now so these are the two cases that we have found out. Okay, so now so as this voltage increases, okay, so this is now in reverse bias condition, and this D1 will be on after some time, especially when V in minus Vx will be 0.7, and of course we have found out what is the Vx in terms of V in. It is this one, which is V in by 2. Okay, so it will be on at this point, and once it is on, then the drop is 0.7, and after it is on, as we keep increasing the V in, then this will reach to breakdown when Vx minus V out will be the breakdown voltage, which in this case it is given to be 3 volt. Okay, so let's analyze this one in the positive half. Okay, so the next condition is D1 will be turned on if my V in minus Vx is equal to 0.7 volt. Okay, and in this case my what is Vx? Vx, we know that it is Vx, we know that it is V in by 2, so let's call this one equation 1. So V in by 2 equal to 0.7 from 1. Okay, so therefore if I just calculate, V in equal to 1.4. so when V in is 1.4 or greater than 1.4, then D1 is on. So when V in is greater than 1.4, so we'll have this following model. So the diode D1 is on already. Okay, but in this case the diode D2 is off, so my R2 will be remaining here, and this is my V in, and this is 0.7 volt drop, and of course this is my R3, and this is my V out. Okay, so in this situation we can easily find out what is the relationship between V out and V in. So in this case we can easily find out the current flowing through this. Okay, current flowing through this I. Okay, and once we know the I, then IR3 will be the V out. Okay, so therefore in this case I, current flowing through this, is V in minus 0.7 by the total resistance, which is R2 plus R3. So again this comes out to be, R2 only, because R2 is much greater than R3. So V in minus 0.7. So therefore my V out is equal to IR3. So this happens to be, if I multiply it, V in minus 0.7 into R2, R3. Okay, so this is comes out to be, R2 into R3. This is 100 by 10k into V in minus 0.7, which is 1 by 100, V in minus 0.7. Okay. Okay, so this was the case when D1 is turned on. Okay, so after the D1 is turned on, see, as we keep increasing this one, so as this Vx almost reaches this, as this associated Vx minus V out reaches 3 volt, okay, then this diode will start, D2 will start breaking down. Okay, so let's analyze this part again. So Zener diode D2 will break down if my Vx minus V out is equal to 3 volt. So what it means is that if the voltage across Vx is greater, like Vx minus V out becomes 3 volt, okay, so it starts breaking down. Okay, so this is the condition. So that means I know that what is what is Vx. So in this case, because this is already on, so now this is the Vx. So Vx will be V in minus 0.7. Okay, implies Vx is equal to V in minus 0.7 minus V out. Okay, what is V out? V out is basically, V out, if you see here, what is V out? V out is, so V out in this case is a voltage Vx by the resistive division. Okay, so this is basically, R3 into Vx by R2 plus R3 equal to 3. So V in minus 0.7, and if you see here, this is Vx is V in minus 0.7, and of course this we have seen multiple times, right? R3 by R2, so this will be, R3 will go away, so it will be just be R2. So it is basically, or if you write it, it is 10 by 10k. Okay, 3 volt. So it is, you should say that it is, B in minus 0.7 by, this is the ratio is 100, so it is 1 by 100 of V in minus 0.7 by 100, okay, equal to 3. So if you just calculate it, we'll get V in to be 3.73. okay, volt. So that means if the V in is greater than 3.73 volt, then D2 is in the breakdown region. Okay, so yeah, so here when all the diodes are turning on, this region is very important. Okay, and according to the equations differs. Okay, so now when my V in is greater than 3.73, so of course D1 is in forward bias region, and D2 is in breakdown region. Okay, so then what happens is my V in is like this. This is my D1, which is having a 0.7, and then we have to replace with the of the Zener diode. Okay, this is given. Okay, and then I have my R3. Okay, this is my V out. Okay, see here in this case also my still R2 is parallel to this, but if you observe here R2, if you observe here this RZ, which is in the problem, it is given to be 20 ohms, and it is much smaller to R2. So RZ parallel R2 will be ultimately RZ only. So this part doesn't come into picture. Okay, we can approximate, because I already have mentioned that if one resistance is much smaller than the other, we can approximate that the value to be the a larger resistance. So what it means is that if RZ parallel R2, so it is RZ into R2. Okay, and this is R2 plus RZ. So because this is much smaller, so it becomes R2 only. So this is RZ R2 R2. So this gets cancelled. So ultimately it is RZ. Okay, so that's why in this case the second part will not come into picture. Okay, so now of course this is the last case, and we can find out the current, and we can find out again the same way. We can find out the total current flowing through this, and I into R3 will be the V out. So therefore my I, or the current I, is equal to this voltage V in minus 0.7. This is 3 volt. Okay, so already 3 volt, and minus 3. Okay, and in the resistance I have R3 plus RZ. Okay, so this comes out to be V in minus 3.7 by RZ plus R3 plus RZ. This is 120. Okay, because RZ is 20 and R3 is 100. Okay, yeah, and therefore my V out will be equal to I into R3 is equal to R3. We know that it is 100 ohms, and this is V in minus 3.7 by 120. So this gets cancelled. This is 5, this is 6, so implies my V out is equal to 5 by 6 V in minus 3.7. Okay, so this is the complete I should say that the transfer function. Okay, so let's write down the different values of the V out. Therefore my V out is equal to, okay, so this is the first, the condition is when it is lesser than 1.38 volt. Okay, 1.38 volt. So when V in is lesser than 1.38 volt, my V out is this one, 1 by 100 V in plus 0.7. 1 by 100 V in plus 0.7 when V in is lesser than 1.38 volt. Okay, so then next, when V in is greater than 1.38 volt or 1.4 uh, approximately, so it is 1 by 200 of V in, and it is still valid till V in is lesser than 1.4 volt. Okay, so so it is V in by 200 when, so this is negative. Okay, V in is greater than minus 1.38 volt but lesser than 1.4 volt. Okay, and of course once it is greater than 1.38 volt, my V out is like this: 1 by 100 of V in minus 0.7. Okay, so 1 by 100 of V in minus 0.7 when V in is greater than 1.4 volt but lesser than this voltage, which is 3.73 volt. 3.73 volt. And okay, let's move to the next page. And finally, this is the one that it is 5 by 6 V in minus 3.7, 5 by 6 V in minus 3.7 when V in is greater than 3.73 volt. Okay, so yeah, so this is the equation, and if you try to plot this, you're supposed to get a continuous curve. And of course, if you see here, the points are really some are very small. Okay, so in one sense, you can almost approximate it to be zero. If someone has approximated to be very small zero, but of course with a proper reasoning, I'll be giving marks to them as well with some little deduction. But if someone has come with a more accurate result, I'll be giving the full marks. Of course, I'll be liberal in the correction because the question was little tough. Yeah, so let's try to draw the transfer function, or even if someone has come to these equations without drawing the transfer functions, I will still be giving the full marks. Okay. Okay, so we have a couple of boundary points. This is minus 1.38 and 1.4 first. So this is let's consider this is minus 1.38, and then here we have 1.4. These are almost this should be almost the similar means. This is 1.4, and then we have the next boundary condition, which is 3.73. okay, so now when it is of course this is easier to plot. Okay, so because it is this is passing through origin, and if we find it out, so of course this points is very small, the slope, because the slope is very small here. This is 1 by 200. Okay, so of course I'll be just roughly trying to draw these points. Okay, so this is 1 by 200, and then the next slope becomes almost double. Okay, so of course this value is very small. If someone has already made it look like a zero, that is also okay. So I have given marks for them as well. Okay, 0.007, and of course I will show you there is an easy way to approximate the whole problem because of this being very small. Okay, so we can easily approximate it. So we can do some approximation directly, and if someone has done the approximation with proper reasoning, I've given marks to them as well. 0.03, this one, if you try to calculate using this equation at this point, and then after this the slope is quite different, so in this case it is the slope here, it is 5/6. Slope is equal to 5/6. Okay, this is really small and this is quite large. Okay, and similarly after this also, if you see here, again this point will be quite similar to minus 0.007. okay, and after this again the slope will increase. Okay, so so this slope and this slope will be same. So the slope here is 1/100, and the slope here is 1/200. Okay, so yeah, so if someone has even because this is a very like a flat line, so if someone has shown a flat and then suddenly increasing to a slope of 5/6, in that course also I have given marks. But if someone is that just directly approximated without writing the equations and all, I have deducted some marks from them. Okay, so this is my VR in and VR. Okay, so now the next question, part B, is I'm supposed to find out the maximum amplitude. Okay, and the maximum amplitude will come especially when this IZM is flowing through it. Okay, so in this equation, if I can write this IZM, okay, and then I'll be able to find out the maximum amplitude. Okay, so basically what I mean is, we have this third case, diode has broken down, and suppose the IZM is flowing for a particular VM. Okay, so I have applied this VM, and then in this case what will flow? IZM is flowing. IZM. Okay, IZM is flowing. Okay, so basically I want to find out that voltage when for which case the IZM is flowing. So we already know that this IZM is, in this case it is given by Vm minus 0.7 minus 3 volt by R3 plus Rz. Okay, so this value we know that it is given, it's already given. Okay, and then we have to find out this one. So if I rearrange it, so this is coming to be Vm minus 3.7, Rz is 20, R3 is 100, so this is 120. So IZM is 50 milliampere. Okay, so this is Vm minus 3.7 by 120. Okay, so if I just multiply it, this is 50 milliampere into 120 ohms, this comes out to be 6 volt. Okay, 0.37 is, because this is in ohms, so this comes out to be 6 volt, and implies my Vm counts out to be 9.7 volt. Okay, so this is the next I should say that this is the next the solution. Okay, and the third point is I'm supposed to draw the waveform. Okay, see waveform and find out the output waveform for this given magnitude of V. So let's try to draw it. Of course, here I have asked to level the y-axis, and of course it is not necessary that you have to draw the the graph in scale, because it's not possible, because we are accommodating a voltage 0.007 and 0.003 something like that, and also high voltage like 9.7 volts. So it is not possible to draw the graph in scale. Okay, so let's consider some different color to show my V in. So this is my V in. Okay, so this is my V in, sine wave V in, and the amplitude is given to be, same as the Vm, which is equal to, this is equal to 9.7 volt. Okay, so now of course, based on this equation, we know that till this point it is really small. Okay, so it is 0.003. So till this is 1.4, the output is 0.7. So maybe let's call it, let's give this, so till my V in is 1.4. Okay, I have 1.4, and here I have 3.73. Okay, 3.73. If you observe my V out is really small. So at this point, if I'm trying to plot the V in V out in the same point, so it will be, it's very small basically. So here in this case, it is going from, going till, at this point it is almost 0.7, and till this point it is 0.3. Okay, so in this case it is, so this point is 0.007, and this next point is 0.03. Okay, and after that it starts rising, and we know that when it goes to 9.7, when 9.7 is here, so if you see here in this case, what will be my output voltage, so we can easily find out. So when when it is reaching BZ Vm, so the current flowing through here is 50 milliampere, and we know that the R3 is 100 ohms. So at Vm, V out will be equal to Izm into R3. So this is 50 milliampere into 100 ohms. So this comes out to be 5 volt. Okay, so more than these 2 points, the indication of this 5 volt is very important. Okay, so basically what I want is voltages. Okay, so the voltage here, it is 5 volt. Okay, so again the same situation will repeat here. Okay, so till this is 1.3 volt, so it will be something like similar here, and then I should say that when this is minus 1.38, so it will also be very small here again. So output again in this case, so this is again minus 0.007. Okay, and of course in this case there will be a peak value in the other side. So especially when it is reaching, V in to be at negative minus 9.7, so I need to follow this equation. Okay, so basically what it means is that when V in is equal to here at this point minus 9.7 volt, my V out will be equal to, I need to follow this expression. Okay, so it is 1 by 100 into minus 9.7 plus 0.7. Okay, So this value comes out to be, so this comes out to be 0.09. Okay, so what it means is that, so it reaches this peak value 0.09. Okay, so yeah, so of course these points are very small. Okay, so and this value is much smaller compared to this one. So if someone have drawn it, actually if in scale, it should look like something, something like this and something like this. Okay, so and if someone has marked this one as 5 volt, I'll be giving marks to them. Okay, of course maybe with little reduction, because I need to justify to those who have done the approximate exact value of this one. So yeah, I'll also be giving marks to them, but with some deduction. But actually overall, if you see, this problem can be, you can even I have done a lot of calculations here, but even if you don't do calculations, we can still come to this conclusion of this one here very directly, because of because this R3 being very small to R1 and R2, it's very easy to do the approximation. So let's you can easily directly come to that conclusion by doing a very crude approximation. Okay, so let's see how. So you see, we have this this one. So R1 and R2 are very large compared to R3. So if you see this voltage division wise, if one of these if one of them is off, right, not both of them are on, right, so the voltage division is going to happen as R3 by the V out is going to happen R3 by some like R1 or R2, right, if one of them is on. So that means my V out is going to become very small if one of these two resistance is active. I mean if one of these two diode is off. So from this we can clearly say, right, so what I mean is when V in is much negative, this is always off. So I am going to get a ratio of R3 by R1 definitely, so which is very small, 1 by 100 we have seen it, so it's almost 0. So what I mean is that if we draw this curve also, right, V out V in, we can approximately say that when V in is negative, the V out by V in is almost 0, because this R1 is on. Okay, R1 this D1 is off and R1 is active. Similarly, till the time this is not breaking down, which is happening at 3.73, so initially this will be active, but still this will not be active, this will be in reverse bias condition, and this R2 resistance will be active. So till this point, till this point 3.73, I can again assume this V out to be much smaller than V in, so it is almost 0. Then this also we have seen the accurate analysis. Okay, accurate analysis, that the slope here is almost very small, okay, till this point, and of course, so and of course once it is on, we can easily find out the slope, but then the slope is 5 by 6. Okay, 5 by 6, then it is like close to 1, of course. So then it is the actual V out is changing with respect to V in, otherwise before it was much small. So one can directly come to this also as well, and from there also you can approximately draw the graph. So whoever have done this kind of approximation, I have not given full marks, but I have given more than 80% marks to them as well. Okay, so 80 to 90% marks I have given who has justified with proper explanation. If someone is justified with proper full explanation, definitely I'll give them full marks. Again, the approximation should be with a proper justification.